Now, rings have their own sort of special place in organic chemists' heart, and that is because they're pretty unique in the fact that they're all made of sp3 carbons, like for instance, cyclohexane is pretty known, you know that by now. Cyclohexane right here is a pretty well-known configuration. And of course, this is all sp3, right? You should be able to just rotate that all the way around, but you can't, because if you tried to rotate that around, I don't even know what would happen. How would you do that? So you got these things right here, you got hydrogens here and here, and you would make something that looks like that. I don't know. So you can't really do that sort of typical bond rotation that we did in the prior lecture. What you do instead in a six-membered ring is you change the physical conformation of a ring, right? So this is obviously, cyclohexane is obviously not a two-dimensional structure. It's 3 dimensions. So it's going to have pretty profound changes on the configuration of that ring. So you're going to have a lot of different configurational isomers. Of course, cyclohexane is not the only compound, right? The only ring compound that we really talk about. We've got cyclopropane, we've got cyclobutane, we've got cyclopentane, we've got cyclohexane, and we've got cycloheptane. And if you get a PhD in organic chemistry, you can draw these shapes very quickly, just like I do. And you know, they're all just ensconced in hydrogens, of course. I really don't want to draw them all out because that would be tedious. But they definitely are. And we talked about how to name them and what they're all about. What we didn't really get into is sort of, you know, when we look at these, when we look at these, that we can't treat them equally, right? Because we've said the bond distance in an sp3 hybridized configuration is 109.5. So a tetrahedral carbon, sp3 hybridized, is 109.5, which obviously, if you went to triangle school like I did, you would know that this is an equilateral triangle. At least I hope it is, because that's what I just said. And that these triangles have 60-degree angles on the inside. That's a far cry away from 109. So if you want to consider total ring strain, how ring strain as a term that is essentially how much energy is locked into this because you've moved away from the ideal ring strain. The ring strain of this relative to the most unstrained ring you can imagine, which is cyclohexane. Cyclohexane has absolutely zero ring strain in it. And I'll explain why. Because obviously this is a hexagon, so those are 109.5 degree angles as I've drawn them. But surprise, they are 109.5. I hope you didn't just spit out your juice. Yeah, hearing that. Now, the cyclopropane ring strain relative to cyclohexane is 27.6 kcals per mole, all right? Higher than cyclohexane, all right? And cyclobutane has at 90-degree angles, right? So still not brilliant. It's a little less strained, 26.4, but not great. Cyclopentane, you know, you're seeing a trend here. It goes down just a tiny bit. Cyclopentane, you can imagine, there's clearly something goofy starting to go on, because cyclopentane is actually only 6.5 kcals per mole, more strained than cyclohexane. And you get to these bigger rings, they go back up. Right? So they go back up. And something funny is clearly going on in these ring strains. What exactly is causing the ring strain associated with these molecules? And when we take a look at cyclopropane, you know, obviously, in addition to the fact that we have this ridiculous ring strain, if we use the old eyeball of science here to look down one of those configurations, what we see is we have we can draw a hydrogen on this side, a hydrogen on this side, and then that, we'll draw a line here, that is going to go over here to that carbon, so that'll be over here, CH2. And then looking behind it, in order for this carbon, this bond right here, to connect to each other, it's got to be like totally eclipsed and connected there. And so you have like an uber unescapably eclipsed system. So in addition to mad eclipsing, you've also got essentially small bond angles and a torsional strain associated with the fact that these hydrogens are like, ouch, get away. Right? And that gets no better with cyclopropane, right? So once again, we'll draw in our hydrogens here and our hydrogens here. And using the old eyeball of science, stare down there. And again, sort of keep these highlighted because we're going to have to remember where these are going. Now these, of course, are actually, why not use both eyes? We were given two eyeballs, so why don't we just look down both at the same time? And then what happens if we do that is what we see is, let's just say, we'll call this the main eyeball of science here, so we'll just draw this one right here first, is we have hydrogen here, and then we have our red bond that goes over here, and then over there we have a hydrogen here and a hydrogen here. And then we can look down the back of both of those. Whoa, stereo view, right? And then down the back actually is this purple bond that runs in the back. So these are connected like that, which means, again, stupid things eclipsed. So because your purple bond runs like totally eclipsed to your red bond in this thing right here, it's once again eclipsed, and once again 90 degrees, not the desired angle. So the internal angle in a cyclopropane is much closer to idyllic, actually much closer to idyllic than cyclohexane, which you kind of have to assume is 120 degrees. The inside angle of this is what, 108? You know, maybe mathematicians will come out and give me correct me. I don't think so. But what we have is 108 degrees, which is really super close to 109.5. But cyclohexane still has some issues in how it fits together, right? So what we can do, just like with the other ones, is we can still draw our little hydrogens here. And one always has to go up, one always has to go down. That's sort of the rule. And then we draw our little eyeball of science. Oh my goodness, my eyeball. There we go. Now my eyeball of science is healthy. Ooh, almost had to go to like an optometrist for that little guy. All right, so the eyeball of science now, it sees everything. And we're going to have the front one being red, and we're going to have the back one being purple. All right, and we're looking at it from this angle, right? So the front, what we've got here is now a hydrogen and a hydrogen and a red going off here. All right. Now that goes off to this red thing, and the red thing goes up to some sort of white thing, and a white carbon. So that's that CH2 here. All right, and then that has to go back to the purple thing. By another white line. And so we have now the purple connector that goes back here in order to make that work. Of course, that's the bond that's in the back. right? And so we're starting to build our little Newman projection, starting to look pretty good. I should make those a little bit longer. There we go. And then now my Newman projection can be completed because I can, so that's not like perfectly perfect. There, I'm much more happy with that. All right, so this is looking a little bit more eclipsed than probably you'd want it to be. If we sort of imagine that goes down here, that goes right there. It's not 100% eclipsed. It's not 100% staggered either. I mean, I guess I could really force it to look staggered. I have not gleaned anything from this. I obviously know that there's some conformational issues with cyclopentane, and that cyclopentane really likes to adopt this weird looking envelope structure where it's got a hydrogen coming out here and a hydrogen going out here, and then you got a hydrogen down here and a hydrogen down here and here. So, you know, cyclopentane does sort of escape some of the extreme eclipsed here, but not 100%. It's got decent looking bond angles, and it can pucker into this envelope. Now, cyclohexane is a unique structure. It has zero. It's the lowest strain energy. It's sort of what one considers idyllic in terms of its association, and that must mean it does not form a 120-degree bond angle because that's pretty far away from the ideal 109. So the question is, how does cyclohexane adopt this ideal conformation? And its configuration is not an envelope. Its configuration actually is this weird looking chair shape. So it has this bend in it, all right, and it ends up looking like that. And there's a hydrogen that comes down here and goes over there, and then that one goes up, so it's got a hydrogen over here and a hydrogen going up here, and one coming out there, and then that's going to have a hydrogen going down here, and it's going to have a hydrogen going down here, which means there's a hydrogen going up here and here. I mean, that's like the hydrogens aren't, and I will show you in a beautiful GIF in just a second. The hydrogens are like perfectly staggered. Like if you had your eyeball of science, and I'll do the whole Newman projection on cyclohexane, those are perfectly staggered. And when you draw it in this weirdly angled configuration, these now are way closer. These now have a bond angle of like 114. Oh, I'm sorry, they have a bond angle of 111.4. So these are super close to ideal. And there's some conformational shenaniganry with this thing. So all of these things are actually dynamic, right? So you would imagine, you know, there's not a lot of dynamics that like you can't imagine. There's no significant rotation of this hydrogen relative to this hydrogen. They're conformationally locked. There's no, I mean, these hydrogens will always be doomed to stare at each other in an extreme eclipse format. But you can imagine in cyclopentane, and I point this out, that this little envelope, you know, the envelope can actually flip down this way, right? So that this hydrogen, which is always like looking at that hydrogen, you're like, you know what? Your face is ugly. And then this hydrogen can just like flip down, and then that hydrogen can stare at those hydrogens, right? So you can have some pretty good dynamics in this much more flexible 5-membered ring. Now, this is the epitome of flexible. The 6-membered ring is super flexible, and so these things can flip all over the place. Like this hydrogen looking down can go up here, and that hydrogen can go down there. And what you actually have is a pretty rigorous change in geometries in cyclohexane when that happens. So obviously, as the rings get larger and they become more flexuous, you have more configurational freedom. And cyclohexane has this wonderful little animation that's always associated with it, and how these hydrogens that are normally associated with being down, right? So let's just say I go up here. In fact, let us take this actually pretty nicely drawn chair configuration of cyclohexane, and copy it. All right, and put it down here, and sort of relate how my drawing relates to this animation right here, so that it kind of helps a bit, hopefully. All right, is that you have some configuration where you have hydrogens that start up, essentially pointing straight up. See, you can see actually the way I've drawn it, you've got hydrogens just like stick straight up. And you've got hydrogens that essentially stick straight down as well. Okay, and those hydrogens I draw also in red. There's one little hydrogen over there. All right, and now you got hydrogens that kind of stick out. They like stick out to the side. All right, and that's what these are. And they just sort of plunk out here, and they plunk down here. Right, and these hydrogens actually can interconvert, and that's what this GIF is showing. Is you have a hydrogen that starts out equatorial, and I'm sorry. These hydrogens have a name, okay? So these things that stick out looking at you on that sort of periphery here are called equatorial. So the hydrogens that sort of surround the outside are equatorial. And then the hydrogens that stick straight up, these are called axial. Just like these are down here, these three down here, these are all called axial. And so you have 6 axial and 6 equatorial hydrogens, okay? And through a little dance of cyclohexanes, they can interconvert. And that is what this animation is showing down here. Now you note the interconversion that you're seeing. So you're seeing essentially, sometimes it mixes, sometimes you've got the blue all up, and so now it's going to there you go, now you got all the red up, now it's going down, and now the blue are about to pop up. There goes the blue, doop, 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 and then that one goes from the top, and that's falling down, and now now the blue in this particular case are all axial, and then the red goes back down right here. See, now the red is pointing straight down, and these are pointing straight up, and then this one follows. And now that one's pointing straight up, and those are pointing straight. Now these are now equatorial and pointing out towards, you know, the equator, right? So there's this what's called a chair flip. Okay, and you can see it kind of goes through several different sort of intermediate stages. And the first stage, one of the stages it clearly appears to start out with, is one in which all of the red are axial. All right, so you have this axial shape, and that is our typical chair configuration. And why don't you practice drawing a chair configuration too? When you draw this, you can see I've got, you know, come here, make a little line, make it a little jiggy jaggy over, and then go back down, make a little jiggy jag down that way, and then make a little jiggy jog down there, boink, right? And now you can draw in, and I'm just going to keep track of the red ones because, well, no good reason, truly. But these are pointing straight up. And there is a defined process for how all these are actually going to go from being in this axial configuration into the equatorial configuration. And we can see, back in our animation, that it's now one side of the chair is essentially flipping down, okay? And it goes into this intermediate configuration. And this intermediate configuration is actually called a boat. So in a boat configuration, this is your medium energy, or somewhere on your energetic landscape as it tries to get all the blue ones to become axial and the red ones become equatorial. You can draw these two. That goes up, goes over here, goes back down, goes over here, goes down. All right? And so if you draw it like that, you go up, jiggy jog, up to do, and then donk. Right? And now you can keep track of your reds, right? So that's still pointing down. These are still basically pointing up, but now these are pointing more like outward into like the ether, all right, out facing that way. If I were to draw the blue ones, these are now the axial ones. Okay, so these are now axial. And blue just doesn't really show up on this slate-colored paper, but the slate-colored paper really worked with the GIF, and I love the GIF, so. But I can start to highlight the idea here, right? And so then, obviously, after it does its first, so it goes from its chair into a boat, right? And so once it's in a boat configuration, we can scroll right back up and see that then it does its own little, oh, it's going to go back into a boat. That's super helpful. And then it's going to go and bring the other thing up. All right. And so these are the three configurations, three more or less stable configurations, because now it's back in a chair configuration where if we draw that again, you can see that now the red hydrogens are all equatorial because that points that way and that points that way and that kind of points like back there off to the side. Points that way, that way, that way. And now you can see we're back in a chair configuration, except the red hydrogens are all pointing, you know, equatorially, like on the globe, like they're pointing out from the equator. So these are your three sort of metastable configurations. Now, there is a step that this I've kind of omitted where the distinction between these two, right, where the chair becomes a boat. So if we were to plot the energy landscape of the chair-to-chair conformation as it goes through a boat, as I've just now taught, you want to draw something where you have some sort of initial chair conformation that then goes up through some higher energy boat conformation and then goes down into a chair conformation, right? But that's not the complete story. The chair-to-chair conversion actually has a number of minor steps that go in between chair and boat. So what you saw in that GIF is not perfect, but you can see that there's like other sort of configurations where they move themselves out of the way. They end up twisting around each other. So on the way to a boat, actually, there are a couple of different species. So I think that it's appropriate, but the real actual configuration that these go through, the actual energy landscape that they go through looks more like this. All right. Where you do start out with a chair, and then you have some sort of high energy transition state, and then it goes through some sort of periodic structure. So the boat configuration actually ends up being here in the middle. So your boat actually ends up being here, and then your two chair configurations end up being on the other sides of these. And so that's one chair configuration, and then I've drawn that to look a little, I guess, like they're even, but the other chair is exactly the same. So you'll have to forgive me, and I'll just erase boop, 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 that. All right, and so you have this chair configuration, and there's some minor configurations that sort of exist between these two chair configuration and the boat configuration in order for it to go through. And what you want to do to really convince yourself of these things is to build a model kit, all right? Because it's really hard to even show this, honestly, in a GIF. I've made a couple, and they just sort of look somewhat convincing. But when you put a model in your hand, they're actually a bit more realistic. what you end up with here, that's slightly more stable on its way, intermediate between a chair and a boat, is something called a twist boat. And a twist boat is a bit of a configuration that looks like this. And the twist boat configuration is just slightly lower in energy than the boat configuration, only because it's able to avoid this little bonk right here between these two hydrogens. So it's just slightly lower in energy. And you can see the hydrogens as I've drawn them here, they're still sticking out there, and you still have now your blue hydrogen sort of sticking out here. So there's an intermediate structure that's not super well illustrated, and that's just called the twist boat. And of course, you have to go through another twist boat in order to get out of the, go back to the other side. And then you have these really high energy configurations that we don't really need to draw, but these up here would be called half chairs. And those are available in your book if you're super curious as to exactly the route that it goes through. In brief, you should remember the vocabulary words for these intermediates here: twist boat, half chair. But I would say that the principal driving message is that you go through essentially a process, a dynamic motion, I guess that's redundant, a motion that delivers you from a single chair to another chair conformation. And it goes through essentially a modestly higher energy configuration called a boat. All right? So in cyclohexane, everything is a hydrogen, right? They're all hydrogens. And this energy landscape is simple. In ethane, they were all hydrogens when you did the rotation, right? So you had ethane and they were just hydrogens, and that was super easy because, you apply your eyeball of science. And same thing with propane, even when you made that a little bit different. But you notice things become much more complicated when you went to butane, right? Things got hairy. Well, cyclohexane, because it's in a locked configuration, actually things become pretty goofy pretty fast. And that's because this locked configuration that places things in the axial position means that anything that's in an axial position can bump into each other, particularly when they go through these little dynamics. Like you got a boat configuration, right? So then you got a bunch of stuff that's going to start bumping into each other, which is why your boat's all high energy. And you even have these higher energy half chair configurations, which again are just essentially parts of the ring smashing into each other. And the only time you're really at a low configuration is when you're getting these things really spatially separated from each other. And so when you start to add functionalization to a six-membered ring, you really start to, make it a little mad. But it's not that a six-membered ring doesn't have a way to release that anger cathartically. Let's just consider methyl cyclohexane. All right, so in methyl cyclohexane, we're going to draw our chair configuration. All right, and we're going to throw up our methyl group. And we're going to put the methyl group axial. And we know that if the axial position means that every other carbon is going to be up, right? Because in the axial, you go up, and then you go down, and then you go up, and then this should be down. So that'll be down. And then that back there will be up, and then this will be down. So these are all your axial positions, okay? And then you have your equatorial hydrogens, which are now going to pop out that way. And then that'll be equatorial out that way, and that'll be equatorial. I mean, it's equatorial, but it's like upward equatorial, and that's downward equatorial, and that's upward equatorial, and that's downward equatorial. Okay? And now we can look down these bonds using the old eyeball of science. And, we can, while we're at it, look down that bond, because we got stereo vision, of course. Much like the noble hawk, we can see in stereo. And when we do that, we can now draw our blue hydrogen off to the side. I draw our green hydrogen over here. Actually, you know what? I'm looking down the wrong friggin' thing, right? So let's dump that. That's not the right. We're gonna actually have to look down. If we want to look down this bond back here, we got to look down, because even my eyeballs, like, you really got to position your eyeballs. So my eyeballs, if they're gonna look down that bond, then they're gonna have to look down that bond. All right. So these are my now eyeballs. So now they're both looking down. If I go back here and get these old brown dots here, like, there we go. Now I'm looking down the same bonds. Woo. All right. So if I'm looking down this bond, let's not use red for that one. Let's stick with yellow. I'm looking down that bond. I'm looking down that bond right there, right? So I'm looking down that bond. That means the CH3 is going to be facing up. And then there's that gross green color facing this way, right? And I've got this white bond. Actually, that's my other bond. This white bond, I use my little, that bond right there, I'm going to color it white here, right? And there's my first triad. And this white bond, of course, here, that white bond goes in back to the other direction where my other eyeball of science is, but that's just a CH2. So that's my other, now, that's carbon that's associated with eyeball 2. And if I look at eyeball 2, what have I got? I've got that hydrogen, I got that hydrogen, so I got this gross little green booger here, and I got a blue one here, right? All right, and now I can draw my perspective rings to show that what's behind those carbons, right? All right, and behind those carbons are a blue, let's make that slightly different blue hydrogen here, so that's looking down the yellow bond. There'd be a blue hydrogen down here, and boogery green hydrogen over here, and then this white bond, I'll use my laser pointer at this bond right there. That bond's going to be in the back, and that is a white one. So that one's just going to go up here. That's going to be a CH2, and that's going to go back down here. Okay, so then that makes that. There we go. Now I have a decidedly delightful looking Newman projection. And actually, you know what? Let's just make this really clear, because I'm going to go like, that's carbon, and then that's going to hydrogen here, and that's a hydrogen here, right? And what you notice, actually, is, remember from the gauche discussion, right, where you have a gauche interaction, when you have a CH3, that's a hydrogen, even though they're eclipsed, hydrogen, hydrogen, that's gauche. And that's like, I don't know, French for awkward? I don't know. I know it's not polite to call someone gauche. So this is a gauche interaction. And gauche makes people sad. How do you get out of going to a gauche configuration? You twist until you are in a full-on anti-configuration, all right? So if you want to twist yourself, you got to do a ring flip. And so, right, ring flip. If something's in the axial position, then move it to the equatorial position. And so I'm not going to draw that crazy amount of motion that's necessary to get the methyl group into an axial position, or sorry, an equatorial position. But you can imagine it involves this green booger-looking hydrogen moving over there, and then this methyl group now collapsing over there, which means that this goes that way. It's all kinds of crazy dynamics in that thing. But the thing is, unlike the cyclohexane, when you've got a methyl group here, it wants to move, because it has this obnoxious, what you call diaxial interaction, right? So this gauche interaction has a very special name, because we can't just give something one name. In a ring, it's called a diaxial interaction. And that interaction occurs with, if I draw this, let me just draw it very clearly. Over here, that hydrogen, I'm just running low on colors. Ooh, no, I've got purple. This hydrogen, draw that hydrogen, right? They're both in the axial configuration with this methyl group. That is a 1,3 diaxial interaction, right? Because we are going 1 carbon, 2 carbon, 3 carbon, 1,3 diaxial interaction, which is why when you have a substrate, in fact, this is so important, I'm going to even write it down. When you have a substituent on cyclohexane, it wants to be equatorial, all right? Because one-three diaxial interactions will drive it that way. Sterics, which is, again, a fancy word for things bumping into each other, demand that it become equatorial, all right? And when it becomes equatorial, then it's not going to bump into each other, right? So if we were to redraw our configuration so that now we have a chair, and now the methyl group is equatorial. In fact, we don't even really need to draw a Newman projection because I could just point this. So if that's equatorial, then this is axial, this is axial, and this is axial, right? So if we, it's got axial hydrogen here, so if we reclaim our, actually that's very specific. So axial up, axial down. So that's an axial down, that's got to be an axial up, that's got to be axial down. And so if we redo our eyeballs of science, looking through here, and looking down here, and we color these specifically to say that that's the yellow and that's the orange. So we're looking down the yellow and the orange bonds at the same time, right? And so we've got our CH3 coming over here. All right, and then we've got a prohydrogen that's coming straight up. And then we've got this bond here. That's going to come down here and go back up. So that's our yellow. All right, and in the back, we have another interaction that goes that way. So that's going to go up. And then we can actually just fill in. So this is looking down the orange bond right here. And those are just hydrogens. Go down here and here. And then we have our perspective arrows, and those go here. And you have a hydrogen and a hydrogen. And now you see no longer gauche. Anti.